For our first well ordering problem, we're going to look at this set, so the subset of n. We want to apply the well ordering principle to find the smallest element of it. So what is this set at the start? It is the collection of natural numbers that can be written in the form m squared minus 10m plus 28 for some m and z. So let's remind ourselves how we apply the well ordering principle. To apply the well ordering principle, what we need is we need to show, let's call this set S. We need to first show that S is not empty. Once we show S is not empty, the well ordering principle is going to guarantee that a smallest element exists, and then we need to go and search for it. It doesn't tell us how to find it, it just tells us it exists. So let's first show that it's not empty. That is, we want to show that at least one n can be written in this form. And we'll look at the graph on the right in a second. Well, let's plug in an integer and see what we get. So what happens? So again, we need to write our n's as m squared minus 10m plus 8. So one way to find such n's is to plug in integers m. So what happens if we let m be 0? Well, then m squared minus 10m plus, well, let's just plug in 0 actually. 0 squared minus 10 times 0 plus 28 is a natural number. So what this is telling us is that 28 is an S, because we can write 28 as a number, an integer squared minus 10 times that integer plus 28. So this tells us then that S is not empty. In fact, it has 28 in it. Now, at this point, we know that a least element exists, but just to make it clear what elements of S look like, let's try another m. Let's try m is, I don't know, -1. Right, m is allowed to be integers, so it can be negative. So what would happen if we were to, say, square m and subtract 10 times m and then add 28? Well, I think we get 1 plus 10 plus 28, which is 39, which is in fact also an integer. So 39 is a natural number. Scroll down a little bit. So this tells us that 39 is an S, because we can write it as an integer squared minus 10 times an integer plus 28. So this is telling us then that S, has the elements 28 and it has 39. And in fact, it has more than that, but these are what some of the elements in S look like, and this is how you show those elements are in fact in S. You find an integer that when you plug it into our expression, we get the corresponding natural number. Now, let's scroll back up here for a second. The expression that defines our natural numbers is actually a parabola. And that parabola opens up because the coefficient of m squared is positive. And since it opens up, the minimum of that parabola happens if this was like a times m squared plus bm plus c. The minimum happens, well, the x value happens, or the min m value happens at negative b over 2a from basic parabola graphing, or you can apply calculus or however you learned it. And so that's 10 over 2, which is 5. So the minimum for the parabola happens at 5. However, we need to check that when we plug in 5, what we get is actually a natural number. So let's plug in 5 into that expression. So we're going to use geometry to find, well, to guess what the smallest n is when m equals 5. We just need to check that we get a natural number out of it. That is, we need to get something non-negative. So when m is 5, we're looking at 5 squared minus 10 times 5 plus 28. And so that's 25 minus 50 plus 28. And that is, if I can do math this morning, that's 3. So the minimum value seems to happen, or the least element of S seems to be 3, because 3 is a natural number. And we learned that 3 is the minimum from what we know about parabolas. In the picture up here, so this is the answer. 3 is the least element. Or I actually should, let's write that a little bit better. So 3, so this is the minimum of the parabola, plus 3 is the least element of S. Okay, and this is our answer here. Now, let's go back up and let's look at this set. This is often how the well-ordering principle is applied. Namely, we have this complicated set, and we maybe, for whatever reason, are looking for a least element. Later on, when we have more complicated structures, this set will even be a little bit more convoluted. And usually you don't actually care about what the least element is, just that a least element exists, and then you use the fact that it's a least element. But I wanted to show you this example because it's a non-trivial example of applying the well-ordering principle.